Hey everybody, Dr. A here, and in this video we are going to explore a third example of axial deformation. If you haven't seen some of the other examples, you can take a look. I've got a first and second example related to axial deformation that could be of use to you as well. So let's take a look at this given information. Here we're saying for the bar below supporting the applied load and subject to a temperature increase of 37 degrees Fahrenheit, compute the axial deformation. So we have this bar here, this axially loaded bar, and again, we know it's axially loaded because the applied force 2.5 kips is directed along the longitudinal axis of the member. It's 14 inches long. And it has the following properties over here. It has a modulus of elasticity of 29,000 KSI. It has a cross-section diameter of 2 inches. And then it has a coefficient of thermal deformation of 6.6 times 10 to the negative 6, 1 over degrees Fahrenheit. Okay, so we're given all of its properties. Again, this is a cross-section diameter. So if you look inside a cut section here, then its diameter, it's a circular cross section, so it's a rod of some sort, 2-inch diameter. So now that we know what we're looking at, let's go ahead and write solution here. So the first thing I like to do in most of these problems is write my governing equation. So I know I'm going to have deformation due to both applied load and thermal effects. So I'm going to write delta equals PL over AE plus alpha delta TL, okay? Now, I don't need the integral form because all of my given information for this problem is constant, and I also don't need the summation form because I have one segment. I have one segment, and this one segment has all constant properties, okay? If I had multiple segments or if I had multiple domains with things changing, you know, with different cross-section areas or different internal loads, then I would need the summation version of this. But I just have one segment that everything is constant within my one and only segment. So I don't need the summation form of this, but I do need the force version, the force form of deformation, and the thermal form of deformation because I have an applied load and a change in temperature, okay? So let's take a look here. What do we know right off the bat? Well, I can check off, I know the length of the member is 14 inches. I got that. I know the change in temperature, right? I know the change in temperature that was told to me in the problem statement, 37 degrees Fahrenheit. I know the coefficient of thermal expansion or thermal deformation is given here as this alpha value. And I know the modulus of elasticity, that's given here, 29,000 KSI. I don't exactly know area, but I pretty much know what I need to find area. So let's go ahead and calculate that right now. It's a circular cross section. You know that because it tells you that D equals 2 inches, and that's a diameter, and really only circles have diameters. So you could say pi D squared over 4, and of course that's pi times 2 inches squared over 4, and so that just comes out to be 3.14159 square inches, or you could just say area is about equal to 3.14 square inches. So it just so happens that we have a nice convenient cancellation of 2 squared with a 4 here, so your area is basically pi. So now we have area, right? We can check that off. Now, what about P? What about this internal load P? Well, in this case, since you only have one segment and you only have one applied load, then your internal load is going to be the 2.5 kips. Now, if you're not convinced of that, you can use method of sections. I discussed this in one of my previous examples. You can make a cut section somewhere in this member, and you draw here your known 2.5 kips, and then coming out of your cut section is P, and then of course you say sum of the forces in the x direction equals 0, and we see that P is equal to 2.5 kips, and it will be a tensile effect. So that's a very obvious and simple method of sections step. And like I said, if you just see that you only have one segment with one applied load, then the internal force must be the 2.5 kips. But again, you can show that using method of sections just to convince yourself. So, so that gives us what P is. So now we're ready to go. We're ready to calculate this deformation. So I'm going to say delta equals 2.5 kips times 14 inches, all divided by 3.14 square inches times 29,000 kips per square inch. So that's the KSI, plus my alpha value 6.6 times 10 to the minus 6, 1 over degrees Fahrenheit, times 37 degrees Fahrenheit, times 14 inches, okay? And so let's make sure our units make sense. We can see that our square inches in the 29,000 KSI cancel with the square inches in the area, and then my kips from the 29,000 KSI cancel with the kips in the numerator of that first term, so we're left with units of inches here. And then again in my second term, the degrees Fahrenheit cancel with the degrees Fahrenheit here, and you're just left with inches in the second term. Again, this is a deformation calculation, so your final answer, you got to think about it, your final answer should have units of length, of an amount of deformation, length, and in this case, inches. So let's go ahead and let's color coordinate. Say delta equals, I'm going to use my TI-36X Pro calculator. So I got 2.5 times 14 divided by my area, and then divided by 29,000. Go slow in your calculator. Don't try to be a hero with these calculations. You'll make a mistake. So you got 0.0003844 inches as the first term. And then let's look at the second term. We have 6.6 times 10 raised to the negative 6th power. And we're going to multiply that by 37. And then we're going to multiply that by 14. And so we get a thermal deformation of 0.003419 inches. And we can add these two together, and we will get the following total deformation as 0.003803 inches, and that's going to be an elongation. And we know that that's going to be an elongation because that applied load of 2.5 kips is causing this thing to stretch. This is going to stretch out. And then whenever you have an increase in temperature, if you just look at our governing formula, a positive or increase in temperature generally would cause an expansion of your material. So one thing to note here is that if you just look at these two values, which one of these values is actually causing more deformation? Well, the thermal effects, okay? So we can make a little side note here. The change in temp is causing a larger deformation or expansion compared to the applied load. So a nice conceptual observation here, and in this particular example, this 37-degree increase in temperature, which really isn't that much. I mean, we see 37-degree temperature differences between winter and summer all the time. That's causing this thing to deform more than the applied load, which is pretty interesting. Now, this is still a very small number. 0.0038 inches is still a small number. But that's it. That's going to conclude this example. So please hit like and subscribe.